Now, we've already looked at all the different pieces and parts for motion graphs and how to transition between them, but there's actually a lot more information available inside of a motion graph. Specifically, that information is found in the slope and in the area under the curve. Now, all of the information we're about to go over, I'm actually going to derive in class to prove that it's true, but for now, let me just go ahead and give this to you. In a position time, here, xt, the slope of any line here is the velocity. So whenever you need to know the velocity of an object, it's actually the slope of that line. And in a velocity time graph, vt, the slope is the acceleration, and the area under is the displacement. So if you were to imagine here, this could make a triangle shape here. Imagine cutting this down to the x-axis and creating a triangle here. You'll see that in an example problem. The area under is the displacement. And in an acceleration time graph, the area under is the change in the velocity. Now this should, even before I go through the proofs in class, make some sense to you here, because the definition of velocity is the rate of change of displacement, and rate of change means slope. So the slope in a position time graph, the rate of change of displacement, is going to be my velocity. Same thing with velocity time. Acceleration, the definition, is the rate of change of velocity. Rate of change means slope. So the rate of change of velocity is acceleration. The slope in a velocity time graph is the acceleration. Now, these are things you would have to memorize here, but little graphic that might be able to help us memorize this. If you write S for displacement, V for velocity, and then A for acceleration, draw arrows going down and write slope, and then arrows going up and write area under, you already have it memorized. For example, if I have a velocity time graph and I want to find the acceleration, put your finger on the type of graph that you have. Right now we have a velocity time graph, and we want to find the acceleration. Follow the arrow to the spot where you get your answer. That's the arrow down to the acceleration. That means I need to use the slope. Or maybe I have an acceleration time graph. Here, put your finger on the type of graph that you have, and then follow the arrow to get what you want. Let's say I want the change in velocity. Follow the arrow up. All right, let's try a couple of example problems now. Number one, what is the object's acceleration between t equals 6 and 9 seconds? So I have a graph here. First thing, whenever you're solving any problem, is to notice what type of graph you have. This is a velocity time graph. So once again, let me say that. The first thing you do anytime you have a motion graph is you look to see what type of graph you have. This is a velocity time graph. So I'm going to go ahead and put my finger here on the velocity part of my little diagram. Next thing, let's see what we're solving for. What is the object's acceleration between t equals 6 and t equals 9 seconds? So with my finger on the velocity part, because it's a velocity time graph, I follow the arrow to acceleration. That's the arrow down. That means I need to get the slope. So in this graph, if I get the slope between t equals 6 and t equals 9 seconds, then I have found the acceleration. Now a shortened way of putting slope is rise over run. And here in this case, from my t equals 6 to my t equals 9, my rise actually wasn't a rise. It went down. In fact, it went down from 3 to 0. So that would be a rise of -3. And then a run, we went from 6 to 9. So that's a run of from 6 to 9, 3, giving me a slope of -1. So I end up with an acceleration, because the slope of a velocity time graph is the acceleration. So I have an acceleration of -1.0 meters per second squared. Two significant figures given in my graph. And I could do this for every line segment in my graph if we so chose. Right here, my rise would be 0. My run would be from 2 to 6, 4. 0 divided by 4 is 0. I'm not accelerating here, which makes sense because we know that piece of a line to be constant velocity or with 0 acceleration. And this piece here, I'd have a positive acceleration, negative over here because we were coming back down, positive deceleration, same as negative acceleration. So a positive acceleration here, rise over run, go up 3 over 2, so 1.5. All right, let's look at number 2. What is the object's average acceleration between t equals 0 and t equals 9 seconds? And so your first reaction might be, all right, so we find the acceleration of each individual piece here, and then we actually need to average them. But check this out. Each piece goes for a different amount of time, meaning that you would have to weight the averages for how long that acceleration occurred. And that sounds pretty bad to me. Remember that average acceleration, or average anything, is going to be total something divided by total of the other. So average acceleration is the total change in velocity, or the final velocity minus the initial velocity, divided by the total time, 9 seconds. But if we actually look at this equation for average acceleration here, we're taking the final velocity, which is over here, minus the initial velocity, which is over there, right? Final's over here, initial's over there, divided by the time it took to get there. Well, that's 2 data points. I have the final velocity and final time, and then the initial velocity and the initial time, which is 0. But that's actually 2 data points here that we're dealing with. And whenever you're doing what's on the y-axis, which is velocity, minus what's on the y-axis, which is velocity, divided by what's on the x-axis, which is time, what we're actually doing is we're getting the slope of the line here. So you can see here in this case, I went ahead and put down to get the average in a motion graph, draw a line between the 2 points, here the last point and the first point. The reason I left it open is what if we wanted the average acceleration between 0 to 6 seconds? That would be from this point to that point, so my line would end up going kind of like this here. But you draw a line between the points, and then you get its slope to get, if it's a velocity time graph, to get the average acceleration, because slope of velocity time is acceleration. If this was a displacement time graph, then to get the average, we get the slope between 2 points, and that would give me the average velocity there. So here, quite obviously, this slope is actually 0 here. Notice it's a flat line, so the average acceleration is going to turn out to be 0 meters per second squared. Number 3 asks, what is the object's displacement between t equals 0 and t equals 9? So first step whenever you're doing any motion graph is always figure out what type of graph you're dealing with. This is a velocity time graph. So knowing now what type of graph we have, let's put our finger on the v because it's velocity time. And now we ask what we're looking for. What is the object's displacement is what we're looking for here in number 3. So follow the arrow that gets me to displacement. It's the arrow up, which is the area under. So I need to get this entire area under the curve. Now, this shape right here doesn't easily lend itself to trying to figure out what the area is, but I can divide this into multiple other shapes, because if I actually draw a line down right here, and if I draw a line down right there, you can see that I have a rectangle and 2 triangles. So if I get the area of this triangle, and then add it to the area of this rectangle, and then get the area of that triangle, and add all those 3 together, then I've got the entire area down here. Remember, the area of a triangle is 1/2 base times height, area of a rectangle, base times height, and then of course, once again, 1/2 base times height. So the first triangle right here, its area 1/2 its base, which is 2, it runs from 0 to 2, times its height of 3, gives me a displacement for this triangular area under of 3. This rectangle right here has a base of 4, not a base of 6. Be very careful. It doesn't have a base of 6, it has a base of 4 because it runs from 2 to 6. That's the base of that rectangle right there, or a base of 4, height of 3, so an area of 12. And this last triangle over here has a base of 3 running from 6 to 9, a height of 3, so that gives me 4.5. Now all I have to do is add all these together, which of course gives me a displacement of 19.5 meters. Looking at my graph though, it looks like I only have 2 significant figures, so I need to round this to 20 meters. Let's look at the last 2 questions, I guess, from the last problem here that might be a little bit more difficult to understand. I think it was relatively easy to understand that here, if like number 1 from the last one, not existing in this problem, that if I have a velocity time graph, which this is, and I wanted to find the acceleration between any segment, the acceleration here or the acceleration there, I would find the slope. But I want to look at a couple others again. What is the object's average acceleration between t equals 0, which is going to be up here, and t equals 8, which is going to be down there? And what we said was whenever you're trying to find average acceleration, you're actually, even though those 2 are connected by all of these different line segments, right, that are of different lengths in time, what you can do instead is you can draw, if you will, a line from the first point to the last point and find its slope to get the average. So here I'm finding the slope of that line, and actually, rise over run here, I didn't actually go up, I went down. I went down from 2 to -3. That's a rise of -5, right? Because I'm actually going down from 2 to -3. And I ran a total of 8 seconds, which would give me an average acceleration, a bar standing for average there, of 0.625 meters per second squared, or if we're going to use sig figs here, because notice the 2 sig figs from the graph, -0.63 meters per second squared. All right, number 2 I'm actually going to do relatively quickly, but I wanted to show this because I wanted to show one that has a lot of different pieces. Number 2, what is the object's displacement between t equals 0 and t equals 10? So step 1, identify what type of graph I have. I have a velocity time graph. Step 2, after I put my finger there on the v, see what we're looking for. We're looking for the displacement. That would be the area under. So I'm going to find the area under the curve, always going down to the x-axis. So it's this entire area, but I also have this entire area that's actually, if you will, between the x-axis and the curve. So going now up from the curve up to the x-axis. So I need all of this area and all of this area. But notice, this area is going to turn out positive because all the heights of my shapes, if you will, are positive, where this area is going to turn out negative because in this area, I have negative velocities, meaning that I am moving backwards, so that would actually subtract away how far I have gone forward in the displacement or give me a negative displacement down here. Now, whenever you're trying to cut things into shapes, try to cut them into rectangles and triangles. Those are just a lot easier. So I see a rectangle there, and whenever I cut right down there, I don't have a single nice rectangle or triangle, but if I cut over there too, all of a sudden now I have 2 rectangles. I have a rectangle on the bottom and a triangle up on top. Then I can cut down right here and get, whenever I cut down right here, now I have a rectangle triangle. Same thing whenever I cut down here at the 8 seconds and then the 10 seconds. So it looks like I have 7 pieces whenever I cut it all up, and if I add up the area of all those 7 pieces, I come out with my total displacement. I'm going to go ahead and work that out for us. So as you can see, I went ahead and I got the areas for each part, 1 through 7. I labeled those, color-coded for us too. Once I get the areas of each individual piece after breaking it up, to find the total displacement of all of those, 0 through 10 seconds, so all the pieces there, I just simply add them. So I end up with a displacement of 9.5 meters after adding them all up. And the one reason that I wanted to do this problem is I wanted to point out whenever you are below the x-axis, you're looking for the area between the curve up to the x-axis, and it is going to turn out with a negative displacement. So you have positives and you have negatives that would end up subtracting out.